My name is Peter Ogden, and I'm an engineer in the Xilinx Research Labs based in Ireland. I've worked on PYNQ for over 3 years, and in the past 9 months, I've been working on bringing PYNQ into the data center. Since its inception, the PYNQ project has been working to make programming FPGAs with embedded processors simpler. With the most recent version, however, we've extended our support to data center acceleration cards. With this presentation, I'm going to give you a quick overview of what PYNQ is, what it means for PYNQ to support compute acceleration, and how PYNQ ties into the rest of the Xilinx compute acceleration solution. We'll only cover PYNQ in the broadest terms here. For more details, there is a companion lab to work through, which can be run either on Amazon's AWS F1 instances or on an Alveo card, and I'd recommend working through those if you want a more in-depth view of our API and capabilities. I'll cover how to get the lab up and running at the end. To start with, I want to give a brief outline of where the PYNQ project came from and what its overall aim is. If we think about the traditional FPGA user base, it consists primarily of hardware engineers and has gradually encompassed system software engineers as platforms like Zinc have integrated embedded processors with the programmable logic. This is not where most people who write code operate. If we look at the explosion in recent years of data scientists and machine learning specialists, the bulk of code being written now lives in a world of high-level programming languages and optimized libraries. There's a reason that high-level languages have succeeded so well in this world of domain experts, namely the increased productivity that comes from having a comprehensive standard library, hundreds of thousands of projects, and languages designed around expressiveness. Coming back to our FPGA world, there's no reason we can't have these benefits when testing and interacting with our own hardware designs. This leads us to the main aim of the PYNQ project, enabling more people to program Xilinx platforms more productively. And I hope you can see how this encompasses both people new to Xilinx platforms coming from machine learning or other specialized domains, while also offering our existing user base tools to get the designs up and running faster. While this project started and got its name from Zinc, nothing I've said is Zinc specific. These same forces and opportunities are present in the data center as well as on embedded devices. So starting with PYNQ 2.5.1, we're expanding the scope of PYNQ to include Xilinx compute acceleration platforms. If you've not used PYNQ before, the experience we gave out of the box consists of providing you with a board and an SD card image. By plugging in the SD card, USB cable, and Ethernet, the board would boot into a full desktop Linux environment. You could then open up a web browser on any device you had to interact with the board and the designs that we supplied with it. While little of this applies directly to a compute accelerator, we can start pulling things out of the experience into what we consider, for want of a better way of putting it, the PYNQ brand. The first and biggest point is to make the getting started process as easy as possible. For each of the embedded platforms we support, there are pre-made SD card images available and videos to help users get set up. We've updated the documentation for PCIe cards, but really our hope is to make the getting started process simple enough that it doesn't need to be referred to more than once. The second aspect is making it easy to install new designs. We've maintained a list of community projects on our website, each of which links to a GitHub repository from where the project can be installed. Installing a project like this not only delivers the code, but also the FPGA bitstream and IPython notebooks, which offer an interactive way for users of the project to learn about and experiment with the design they just installed. In the past, we offered guidelines for project developers on how to package their designs, but with the move to x86 and the data center, we now have dedicated support for including notebooks and bitstreams inside of a Python project. This means we can easily put projects onto the Python package index or PyPI, making the install process even easier for end users. Finally, we have the APIs themselves, which have been carried over from our embedded platforms. The aim is not to provide a competitor for OpenCL, but rather to give a high-level API that resembles the hardware. As an example, we still want to be able to query the registers on an accelerator when things are not going as expected. That's not to say that the only way to invoke hardware kernels is by poking registers. We can now call accelerators with arguments, the same as you would for OpenCL, which makes a lot of compute acceleration code simpler, but we want to be able to do that without needing to reason about execution queues and other high-level abstractions. I've talked a lot about notebooks so far, and that's because Jupyter and the notebook were key enabling technologies for PYNQ. It gave us the out-of-the-box, interactive experience that didn't need any Xilinx tools to be installed. Jupyter grew out of the IPython project, creating an environment where multiple languages, including Julia and R, from where Jupyter gets its name, can be executed in a browser. It's more than just creating code in a browser, though. It's about being able to create a reproducible document, including notes written in Markdown, the results of executed code visualized using graphics or other multimedia, and having all of the code needed to produce those outputs included in one place. In giving the Jupyter project their Software System Award in 2017, the ACM noted that Jupyter has become a de facto standard for data analysis in research, education, journalism, and industry. At this time, 3 years ago, the number of notebooks in GitHub was just over 2 million. Since then, this has grown to more than 7 million, cementing the notebook as a key format of data science. Open source projects don't stand still, however, and since 2017, the Jupyter project has been working on Jupyter Lab, the successor to Jupyter, which incorporates an even richer set of features. Jupyter Lab acts as an IDE for notebooks, with a full document and window management interface. As a result, parts of notebooks can now be split out to show different visualizations, terminals, both Python and System Shell, can be viewed alongside notebooks, and the built-in text editor is rapidly gaining features such as debug support. Jupyter Lab also has a rich ecosystem of extensions with support for multiple interactive plotting frameworks, distributed server management, and editing tools already among those available. This lab introduces Jupyter Lab, but only scratches the surface of its capabilities, and I highly recommend checking out the Jupyter Lab community to learn more about it. It's all very well talking about Jupyter and Python, but we still need an API to access the hardware. Here we've taken our PYNQ APIs for embedded processors and ported it to the data center with a couple of additions to try and make the process of calling hardware kernels as painless as possible. From our other training material, we've identified 7 steps that form the core of any software that wants to use an accelerator card in a heterogeneous system. There's almost an exact one-to-one mapping between these steps and PYNQ function calls, with the exception of the first 2, which are combined under a single import statement. First step is creating the overlay object, which downloads the bitstream, as well as enumerating all of the objects, be they memory banks or hardware kernels, in the design. With the bitstream downloaded, allocating and managing buffers on the card is done through NumPy arrays returned by our allocate function. Each array is a pair of host and device buffers, so populating the buffer with data works the same as any other NumPy array, with the addition of functions to synchronize the underlying host and device buffers. Finally, we have a single function call which executes the hardware kernel. There's a lot more depth to the APIs than is shown here, which is covered in the lab material, but I wanted to give you a sense of the flow of a PYNQ program before heading in. One thing to note is that there is no cleanup code specified. We make use of Python as a high-level, garbage-collected language to free hardware resources when they are no longer accessible, meaning that in most cases you don't need to worry about exactly how and when to free resources. One question that comes up is how PYNQ relates to Vitis and the unified development platform that Xilinx is developing. PYNQ as a software framework sits on top of the existing hardware and software tools as any other application would. We rely on the V++ hardware compiler to generate bitstreams that are understandable by PYNQ, and on the low-level Xilinx runtime to interact with the hardware. PYNQ is complementary to these flows by providing a way for a generic design to be driven in a high-level language. With all that said, by far the best way to understand what PYNQ for computer acceleration means is to try it for yourself. The lab is structured as follows. The first 3 steps are all about getting PYNQ installed and Jupyter Lab running. We recommend installing PYNQ into an Anaconda environment, as that handles all of the dependencies for Jupyter Lab for you. The lab itself is broken into 3 parts. First is an introduction to the common APIs, which goes over some of the parts of this presentation in more detail. Next, we have a notebook on how to optimize host code. The techniques outlined here aren't PYNQ specific, but Python provides a good environment for experimenting with how different coding styles impact performance. Finally, we explore a design built on one of the Vitis libraries for compressing data using the LZ4 format. The only URL you need is the one which links to our Python package for this lab. On that page, you'll find the rest of these instructions you can copy and paste to complete the installation of the lab. First, you should install and activate Anaconda, which will install Python, Jupyter Lab, and a number of other packages. With the Conda environment active, you can then install PYNQ and the lab package. The PYNQ get notebooks command will create a PYNQ notebooks folder with all of the lab material in it, and from there you can start Jupyter Lab. This will cause a browser to appear, and double-clicking on the introduction.ipynb will bring up all of the documentation you need to start programming with PYNQ. There's also an Introduction to Jupyter Lab notebook, which I recommend reading if you're completely new to the environment, as it explains how to edit and execute code inside the notebook. Each of the 3 lab notebooks has a mix of documentation and code examples, with 3 exercises at the bottom to give you an opportunity to experiment with the concepts presented. Once you've finished, check out the Resources notebook for links to further examples and documentation. That completes the presentation portion of the lab. There are some short additional presentations linked in the Python package documentation where you found the install instructions. These will give some insight into the other features of PYNQ that aren't included in the main set of labs. We would encourage you to join our forum if you have any questions or comments, or if you have a design you wish to share. We are always on the lookout for new acceleration designs to promote.